12 o'clock, two classes. In between which
Tuesday we have program elective, sir, so it's not
no,
possible.
no, Friday.
Yes, sir. Friday we have 10 to 10:50.
10 to 10:50 were free. And
Yes,
okay, then next week Tuesday. Okay, let us keep it on Tuesday.
sir. Acha, you are
Yes,
saying about quiz, sir. Next week Tuesday.
that's why I'm going to take some classes so that I can finish at least 90% of the first modules. Then we can announce the quiz.
Yes,
Yeah.
sir.
So that's why. So next week, okay, let us keep it next week, Tuesday. Sorry, Friday, 10 to 10:50, right?
Yes, sir.
Then next week, I'll take your quiz.
Yes, sir.
We'll see if or Saturday or tomorrow you have any free. Tomorrow you're busy.
Yes, sir. Tomorrow we are busy, sir.
Okay, okay, then we'll see. Let us see how far we can cover. Okay,
Yes,
let us
sir.
start. Then we'll say let us keep it to next week Tuesday. Next week Friday, 10 to 10:51 extra class. Okay. And then I have to fast. I have to make fast. The slide is visible to you.
Yes, sir.
Okay. So last times we have seen some basic things, fiber types, basic laws. Right. We have seen that we can use ray optics method. We can use wave optics method to describe the propagation of energy. And in that context, we have seen the phase velocity, group velocity. Those things are also there. Particularly when we discuss the dispersion, those things will be used. So basic things we have seen, other basic laws that you know it. So I don't want to discuss all those things, but whenever those things will be applied when you consider the fiber parameters. So you'll see it, we have seen it whenever multimode fiber will be considered with the large core fibers, that times we'll consider the ray optics method. And whenever dimension is very, very small, that times we will consider the wave optics method or mode optics method. Okay, we'll discuss the fiber parameters, fiber design before mode optics theory. We'll see it, but before that, let us quickly see the fiber materials and fiber fabrications. What are the materials used for fiber fabrications, and what are the different fabrication processes? Right. Here you can see, or I have mentioned, what are the, say all the materials cannot be used for fiber fabrications. The materials that can be used for fiber fabrications, they must have these four requirements. You see the four requirements are there. The first requirement is it must have low refractive index in the cladding and high refractive index in the core, so that it can behave as an waveguide. Right. That's what we know it. Fiber is a waveguide, high refractive index at the core and low refractive index at the cladding. This first requirement for fiber fabrications or materials that will be used. They must have different refractive indices in the core and the clad. Second criteria is the material must be dielectric. Fiber is no fiber. The signal is optical signal, so it is not the conductive element. It is the dielectric materials. The materials we'll see the different materials are there. These materials they must have low loss in the infrared regions. Infrared regions of the electromagnetic wave spectrums. EM spectrometric wave spectrums. We have seen in the large in the very first class I have shown you the electromagnetic spectrums, audio wave to say cosmic ray, etc. But fiber optics is not fiber optics. All the spectrums are not used. Only infrared regions is used, right? Visible also it is not used. Visible is a very lossy. Loss will be high in that case. Only low loss region is infrared regions, so that is used. I mean, it is generally 0.8 to 1.6 micron regions. I have seen the different generations are there within these regions. So you must have low loss in the infrared regions of the electromagnetic wave spectrums. This is the second criterion. the third category is this. We have seen these SI fiber, GI fibers, etc. Particularly for GI fiber, we have seen it. It is for to increase the bandwidth of the fiber. I mean, that is having variable refractive index within the core. So in that case, the core within the core, you have to vary the refractive index. So the materials, when you choose the materials will be such that we can have our a particular profiles. We can create a particular profiles within the core of the fiber to get a large bandwidth fiber. So that's what it is. We can that profile can be alpha profiles, can be a linear. Alpha means is the parabolic profiles, can be parabolic profiles, which is widely used for parabolic profiles or linear profiles, or the step index. It is a constant refractive index. Those things will be there. So the materials property would be such that we can vary the refractive index as per the requirements. I mean, we can create a particular profiles within the core of the fiber to get high bandwidth fiber. That is the third conditions. The fourth condition is this: the metal would be such that we can draw a long, thin, flexible fiber. Right? Probably you have not done. I don't know whether you have done surface tension experiment in the 12 classes. If you see, if a hollow glass tube is there, if you heat it and pull it, it will be just like fibers. But of course, that is hollow ones. Similar things would be there also here. The fiber is heated, then pulled, so that it can be a long, thin fiber can be drawn. It must be flexible. We see if it is made of glass, how it can be flexible. That will see it by using a plastic jacket. Then it will be flexible. So anyway, the materials would be such that we can draw into a long, thin, flexible fiber. There are the four requirements for materials that can be used for fiber fabrications. Now, what are the materials? There are two kinds of materials, can be two types. They can satisfy these requirements. One is the glass, and that is the plastic. Glass, again, glass can be of four types. It can be high silica glass, it can be halide glass, heavy metal fluoride glass, or it can be a chalcogenide glass, or it can be active glass. So there are different glass fibers out there, and this is under the glass. And plastic also, plastic fibers are there. Plastic fibers can be, of course, it can be core can be glass, clad can be plastic, or it can be both core and clad can be plastic. We'll see it. So there are different types of materials are there for fiber fabrications. Now, if you see the first ones, high silica glass. What is this high silica glass? Actually, here the silicon silica. You see, high silica can be two types. Silica glass can be two types: high silica glass or compound silicate glass. In high silica glass, there will be silicon oxide, plus there will be dopants, doped silicon oxide, right? In high silica glass. What are the dopants? You see phosphorus pentoxide, germanium oxide, boron oxide. These are the dopants. If you use these dopants in the silicon oxide, then the refractive index can be varied. Now the question is, which oxide will increase the refractive index, which oxide or dopant will decrease the refractive index? You see the graph in the right hand side. Here you can see it. Here you see refractive index versus the dopant additions. Here you can see it. Here germanium oxide, it increases the refractive index. Phosphorus pentoxide also it increases the refractive index, but boron oxide B2O3, it decreases the refractive index. Also fluorine F, it decreases the refractive. This is x-axis the mole fraction, that is dopant mole fractions, molality, that is mole fraction that is used for that is percentage of additions, dopant additions, mole fractions, right? This x-axis, and this is the refractive index. So depending upon these dopant additions, you see refractive index can vary. So keep in mind, germanium oxide, phosphorus pentoxide, they can increase the refractive index, whereas boron oxide, fluorine, they will decrease the refractive index. So by proper mixing of these dopants, you can vary the refractive index, and it is required. We say core should be of high refractive index, cladding should be of lower refractive index. So generally, your cladding is fixed. Cladding refractive index, actually you will see when you fabricate the fiber, your base material is glass, and on the glass the dopants are used to vary the refractive index. So the core refractive index generally it is the dopant. Dopant is in the core, dopants are used to increase the refractive index, or sometimes it will decrease the refractive, or proper mixing is required to vary the refractive index, right? So dopants are used generally in the core regions. Another type of glass, silica glass is here, that is compound silicate glass. You see it here. One example is Na2O, B2O3, SiO2. This is a compound silicate glass. Here, actually, if you see this high silica glass, for directly here fiber cannot be fabricated here, right? You have to create the preform. I am written it. You see, a ultra pure glass rod. A preform is first made, then glass, then fiber is drawn. But in compound silicate glass, there is no need of preform. So directly you can through melting process you can draw the fibers. But anyway, so the glass, silica glass can be two types. It can be high silica glass. It can be compound silicate glass, right? And they are the dopants that can be used. And keep in mind, these are the you see characteristics of the dopants. They can increase the refractive index or they can decrease the refractive index. Right. Now, if you consider this, the first one, this high silica glass, this one that I mentioned, and you see the here the advantage of this silica glass is the advantage is there, advantage, disadvantage are there. In case of this high silica glass, you see advantages is they will have high transparency and they can have high resistance to breakage, etc. Those things are there in the infrared regions of that is used for fiberoptic systems. That is the advantage of this high silica glass. But the disadvantage is their melting glass is melting point is very high, around 2000 degrees centigrade. Right. So you see, if you require the fabrication of fiber through melting, then it will be a difficult process, right? Otherwise, of course, some vapor deposition techniques are there where you can use the preform, and from that you can draw the fibers. So vapor deposition process is here. But anyway, so these are the advantages and disadvantages what I mentioned. Because of high melting point, it is difficult to fabricate from a molten state, right? So this is the high silica glass. And next you see the halide glass. I told you there are 4 types of glasses are there. High silica glass, halide glass, chalcogenide glass, and active glass. So in case of halide glass, it is actually heavy metal fluoride glass, right? It uses zirconium fluoride is a major component. This is ZrF4. Several constituents are required to make the glass. To make here you see one example of this fluoride glass is jet blend. You see, this is widely used for fluoride glass. That is widely used here. The constituents are, you see, zirconium fluoride, barium fluoride, lanthanum fluoride, aluminum fluoride, and sodium fluoride. So these constituents are required to make the fluoride glass, right? And for fiber, you see, you have to vary the refractive index. In this case, of course, if zirconium fluoride, this ZrF4, if it is replaced by henium fluoride, then refractive index can be varied, and actually that is used for claddings. In this case, it is for used for cladding. But jet lamps, this HAF4 is used to change the refractive index, and that is used for cladding. So this is the constituents of these the halide glass. And the advantage of this glass fiber is very low loss fiber you can have it. Very low loss fiber you can have it. You see, it is 0.001 dB per kilometer. You can have it, right? But the problem is this, the disadvantage is this in this case. You see here, it is difficult to fabricate the long fibers, long preforms. Actually, long length of fiber is difficult. This case, I just mentioned before fiber fabrications, preform is made. Actually, two types of processes are there. One process is you have to make the preforms, and other case you have directly you can have the fiber from molten state. So most of the cases the preform is used. In this case, preform is required. Silica, high silica glass also preform is required. This in that case, very long preform generally it is 1 meter. It is just 1 meter in length and maybe 1 inch in dia, 1 inch, 10 millimeter around 1 inch dia, 1 meter in length and 1 inch in diameter, generally in these forms. So, but with this fluoride glass, difficult to fabricate. So it depends. The length of the fiber depends on the length of the preforms, volume of the preforms, so length of the preforms. So here in this process, it is difficult to fabricate the long preforms, right? That is one disadvantage. Also, another thing is this, it is, I mean, it has during fabrication process, there is a formation of microcrystals. So that will have the drastic effect on scattering losses. So these are the disadvantages of these. So disadvantage is long preform to typical to long preforms. Disadvantage, it is long preforms, typical to fabricate. Another is this, number one. Number two is this, it can form microcrystals that will have that will create the scattering losses, microcrystals that times. So they are the disadvantages of the fluoride glass, right? Another type of glass fiber is used for fiber fabrication, that is chalcogenide glass fibers. This is very useful for optical switching. Some optical elements, optical switching. It is of course it is not used for communications, but for switching. On whenever you need nonlinearity, there are various applications of fiber is based on nonlinearity. You see that nonlinearity is there. Nonlinear we'll discuss at the end of this. I mean, in the fifth model, we'll discuss the nonlinearity is here. You can vary the nonlinearity as per requirement. So that is useful for fabrication of all optical switchings, right? That is applications of chalcogenide glass fibers. In that case, chalcogen elements are used, like say sulfur, selenium, telluriums. These are the chalcogen elements. Right? And the widely used material that is used for chalcogen glass fiber, it is the AS2S3, right? AS2S3, which is chalcogenide element, AS2S3, which is used, right? And for SM fiber, generally core is ASSC. These are the elements that are used, and for cladding, this AS2S3 that is used for claddings, right? So these are the chalcogenide glass fiber. Chalcogen elements are used to get the nonlinearity, which can be used for the optical switchings, other applications. Right. Another is this. You see, another is the plastic fibers. I told you this. You see, active glass, plastic, glass, plastic. These are the glass fibers. There are 4 types of glass we have seen. Next is the plastic fibers. Plastic fibers can be, you see, it can be plastic clad glass fiber. I told you, it can be plastic clad glass fibers, or it can be simple plastic fiber. All all plastic. Core and clad both can be plastic. If it is medium loss fibers, then the core can be glass and core can be glass and clad can be plastic. But if it is lossy fibers, then it is both core and clad can be plastic. Then the question is, if it lossy fiber, then why it is required? Sometimes lossy fiber means where short distance fibers are required for laboratory purpose. Easily you can do the experiment. Glass fiber is difficult to handle and difficult to launch light also within the glass fibers. Their dimension is very, very small. But plastic fiber, you come into the lab, you can see some plastic fibers are there, 1 meter, 2 meter in length. Easily you can handle those plastic fibers. Right. Also, some medical purposes, plastic fibers are used. Right. They are lossy fibers. The loss is high, but easy to handle. Right. Sometimes, for say endoscopy, if glass fiber, if inserted is some, if it breaks, then it will be fatal. But plastic, say it will not affect the human body. So many things are there. Plastic fiber advantages are there for plastic fibers. So it can be, but for so fibers can be three types. You can say, is to keep in mind, very low loss fibers. Low loss fibers that is used for communications. It can be medium loss fibers. Medium loss fibers that can be used also for communication, but not for long distances, short distances. And another is lossy fibers or plastic fibers. That is high loss fibers. You can say low loss, high loss. In that case, high loss fibers that can be used for laboratory experiments or some medical instruments. This high loss fibers, I mean, plastic fibers are there. So in the low loss fibers, both core and clad, they're made of glass. Medium loss fibers, core is made of glass, clad can be plastic. And high loss fibers, both core and clad, they are made of plastic. What are the plastic materials? Polymers are used, you can see it, see polystyrene core, methyl in one category, plastic fibers. Polystyrene core is used, polystyrene materials for core, and methyl methacrylate is used for claddings. Ethyl methacrylate for claddings. That is one type. In another type, you see polymethyl methacrylate. It is used for core, and cladding can be copolymer. That can vary the that can vary the numerical aperture. Actually, this plastic fiber, the advantage is that the numerical aperture, we'll see what is numerical aperture. That is most important parameter of fibers. Here, in plastic fibers, the numerical aperture around 0.5, whereas for glass fibers, it is less than 5. Generally, it is 0.1 to 0.3 in this range. Numerical aperture, right? Numerical aperture physical meaning is how much light can be launched into the fiber. So numerical aperture high means more light can be launched into the fibers. Maximum can be 1. Actually, in numerical aperture, it is nothing but n sine theta. We'll just discuss it. N is generally air. Source is placed in air, so n is 1. And theta, the angle of incidence, acceptance angles. So sin theta maximum value 1. So in numerical aperture, it is maximum can be 1, right? Of course, if it is within the air, within the air, it is okay. But if it is within the liquid with some water, then it will be different, because n is the incident mediums, n will be greater than 1. So in that case, a numerical aperture can be greater than 1. So if you just see all the things together, you see this is the silica fibers we have seen. Can be high silica glass, compound silica glass, halide glass. You see that have very low loss fibers, but difficult to fabricate. Here, silica glass highly the advantage is highly transparent in the infrared regions. Chalcogenide glass it is used for optical elements like optical switching, etc. Right, active glass fibers, active glass fiber. Here you see some rare earth elements that they use, like erbium, neodymiums, praseodymiums. Those are used. These are actually erbiums. These are actually rare earth elements, right? This argon rare earth element are there. these elements are doped within the fibers, and if you use these elements, then these fibers, they can act as an amplifier. I told you optical amplifier is here. It can be semiconductor optical amplifier, can be erbium doped fiber, can be doped fiber amplifier. So those fibers, they can be used for amplifiers, amplifier, or can be used for source also. They can emit light also. That's why it's not an active glass. They can emit light, they can guide light, right? They can amplify the light. So those things are there, active glass fibers, right? So they are the different types of fibers. Now let us see their fabrications. So fiber fabrications, generally two methods are used. One is based on preforms. Preform is nothing but I mean, it is ultra pure glass rod. Rod. It's basically rod. Um, Actually, if you see fabrications, you see this preform, how preform is made. There is, these are the element, these chemical mixtures are there: silicon tetrachloride, germanium chloride, the boron chloride, phosphorus chloride. Vapor phase reaction of these these chemicals, right? They will form the ultra pure glass rod. Whenever vapor phase reaction takes place, then ultra pure glass rod is made, which is called preforms. Ultra pure glass rod, right? And that is called preforms. This preform is then used to make the fibers. This preform can be, you see, I just mentioned, it can be 1 meter in length, 9 to 100 centimeter in length, and can be 10 millimeter in diameters, right? This preform, they will have different dopants also, right? Depending upon your type of fibers, right? This preform, when it's heated around 1500 degrees centigrade to 2000 degrees centigrade, then it will be then fiber will be made. Fiber can be drawn from the preform. We'll see it how preform is made and how fiber is drawn from preforms. So this ultra pure glass rod, it is called preforms, and that preform is made from the vapor phase reaction of these chemicals. So every fabrication, you can see these chemicals are there. So that is the preform fabrication technique. So one method is from the preform, you can make the fibers. Another method is directly melting. Direct melting. The materials would be there for core and clad, and they are melted. And from the melting, directly you can. There is no need of preform here. Fabrication directly you can have the fiber. We'll see it. One method is called DD method. Double crucible method is here. That is used for fiber fabrications. Right. Now, let us focus on these preform fabrications. So before fiber fabrications, you need to fabricate the preforms. And now, how preform is made? Preform can be made by the two techniques. One is inside deposition process, and there is outside deposition process. Well, why it is called inside outside? Because every preform fabrication technique, there will be a glass rod. There can be a solid glass rod, or there can be a hollow glass rod, right? So in this case, inside deposition process, there will be a hollow glass rod will be there, and within the within this glass rod, deposition process occurs. If that is the case, then it is called inside deposition process. What are the methods? The method is MCBD technique, PCBD technique. I'll just show you what are those techniques. Modified chemical vapor deposition technique, and there is plasma activated chemical vapor techniques. MCBD method, PCBD method. These are the inside deposition process. Well, the deposition can be also outside the rod. That times the solid glass rod will be there, and at the outside of this glass rod, deposition occurs. If that is the case, if outside deposition process, then it is called, the deposition can occur outside to the glass materials. It can be at the end, or it can be laterally. So it can be lateral depositions, or it can be axial depositions. So lateral deposition, one method is here, is the OVPP method, outside vapor deposition, vapor phase deposition techniques. Outside vapor phase deposition, OBPO, sometimes it is also called OBPO or OBPD, OBPO, outside vapor phase oxidations. Outside vapor phase oxidations. That is the lateral deposition technique. And axial deposition technique. This is widely used because it has very low loss fibers it can produce. So that is the VAD method, vapor phase axial deposition method. That is outside deposition process. So in this case, deposition occurs outside to the target. So this is a silica glass rod, not within this. In this case, in the first case, deposition occurs within the glass materials. This case, deposition occurs outside the glass materials. Okay, let us see the figure, then it will become more clear. So this is outside deposition process. You can see it here, outside deposition process. Here you can see outside vapor phase oxidations. Here you can see it here. There is a solid. Initially, there will be a solid glass rod. You see it. This is the solid glass rod, which is called mandrel bait rod, and there is a burner, which is moving. You see, burner is there, moving in these directions, right? Moving to and fro, right? This burner is moving, right? So that you can have a certain regions of depositions, right? And in the burner, you see metal halides, just a silicon silicon chloride, boron chloride, phosphorus chloride, etc. Those vapors plus oxygens, they are used to inject for deposition purpose, right? So actually, glass rod is here. When the burner is moving back and forth, then the deposition occurs, and that is called soot, right? So whenever certain deposition occurs, after that, this cutoff, it stops the depositions, and whole thing is heated, and then the glass rod is removed. So we'll get what is remaining, that is called preforms, right? And this preform will have, of course, here it will have a central hole will be there, right? So initially, this method is not, this is the old method. Earlier, the beginning, these methods are used. But here, because of these holes remaining, after removing this, the glass rod, this one, some traffic air bubbles may be there. So that may lead to the loss. Right. And so central hole, because of the central hole, some air bubbles may be there. Right, that will increase the loss. That is the drawback of this method, right? But anyway, this is the preform fabrication technique. We'll just see it, how this preform, after getting this preform, we'll see it how fiber is drawn. This is the method for preform fabrications, right? So this after the certain depositions, this glass rod is removed and whole thing is heated to high temperature, like say 1500 degrees centigrade, 1400 to 1500 degrees centigrade heated. Then it will form a clear glass, the rod, which is called preforms, right? And this preform is then used to draw the fibers. So that is the OBPO method, right? Next, you see vapor phase axial deposition method. I told you, you see, this is VAD method, axial deposition method. This is OBPO method, just to have seen. Next is the axial deposition method. In axial deposition method, you see, initially there will be rod. This rod is here. You see, this rod is here. At the end of this rod, deposition occurs. You see, that's what this rod is here initially, and at the end of this rod, the gases are injected. Oxygen burn through reactant gases are injected through these two burners. One is for cladding and other is for coke, right? These are used for core and clad, right? This is used for cladding. This is used for core. So different mixture of reactant gases are injected so that the deposition occurs at the outside of these target materials and glass rod. And this glass material, it is rotated so that it can have circular symmetry, as well as it is moving upwards. That's what is shown here. It is moving upwards so that you can have a certain depositions, certain length of depositions. So this is the deposition. This is the deposition occurs. You see it here. This deposition, it has the porous structure. Porous structure is here. After the certain length of depositions, it is passed through a ring heater. A ring heater is there. This is a heater, ring heater. That will create the zonal melting. Right. After this, when it passed through this, on the porous structure, porous preforms, passed through this ring heater, it will be a ultra pure rod, which is called preforms. This is preform, and this is used to draw the fiber. This is the actual rod that is used initially. So that is the cases of, that is the techniques for this BHD method. So initially glass rod is here, and at the end of these things, gases are injected for cladding and for core through these burners. And after certain depositions, at the same times the core, when the deposition occurs, deposition is being made. That times the rod is circularly rotated, as well as it is moving upwards, so that you can have a certain length of ultra pure rod, which is called the preforms. Right. This preform, advantage of this method is this is widely used for fiber fabrication technique, because it will have very low loss fibers, because there is no central hole in this case. Central holes that will increase some losses, scattering losses, etc. So there will be no central hole, so no such loss will be there. Very low loss fiber, you can have it. Also very long preform you can make it in this case, which is not possible for other case. Very long preform you can make it. That means very large length of fiber can be drawn. And also another thing is there will be no contamination. Whole thing in a chambers and enclosed chambers, so there is no need of, there is no contamination in this case. Right. That is in a clean environment. It can provide a very clean environment. Right. I mean, the deposition chambers and the zonal meltings, they are highly connected to each others. They're tightly connected to each others. And so in the same enclosures, and that will provide the very clean environment. This right, and that's what, and there'll be very low loss fibers. You can have it. So they're the distinct advantages of the VAD methods. Next, you see the MCVD technique, modified chemical vapor deposition technique. In this case, there will be hollow glass rod. In the previous two cases, there is a solid glass rod, the outside deposition process. This is the inside deposition process, and the hollow glass rod is used. One is MCVD technique, and this is PCVD technique. This is PCVD technique. So in this case, MCVD technique, you see reactant gases are injected from one side, and the rod is rotated cylindrically to get the cylindrical symmetry. Also, this burner is moving back and forth, right? So that you can have a sintered glass. So initially, the soot formation is here. Next, since burner is used for because of this heating case, you see a deposition occurs. That is called the sintered glass. Sinter meaning is this. Sintering means I mean liquidification. Liquidification is avoided. Generally, from particles to solid. Before solid, liquid state is there, but here directly from the soot to the sintered glass solid state is possible, right? So so that is called the sintering process. So sintered glass is directly formed here, and the whole thing, it is heated after certain depositions. Whole thing is heated so that you can have the preforms to get. I mean, whole thing will collapse. It is hollow, so when it is heated at a certain depositions, it will collapse and it will create a solid rod preforms, right? Of course, solid rod preform indicated in this case, right? So that is the preform, and next preform is used to draw the fibers, right? That is MCBD technique. Another inside deposition process is this plasma activated chemical vapor deposition. In this case, a chemical reaction takes place with the help of plasma. So to create plasma, a microwave resonator, microwave heater is used to create plasma, right? I mean, when there is also a hollow tube will be there. When the hollow tube is heated at a temperature in the range of 1200 degrees centigrade, then at that times, and if this micro resonator is moving back and forth, and the frequency it is 2.45 gigahertz, 45 gigahertz, right? At that frequency, it will create a plasma inside the tube to activate the chemical reactions, right? So in the advantage of this method, there will be no soot formation. There is a soot formation. There is a soot formation. There will be no soot formations. Directly, you can have uh, the depositions. Right, deposition occurs. Glass layers will be deposited on the inside wall of the this glass rod. Right. So there is no need of sintering here in this case. There is no soot formations, so there is no need of sinterings process. So sintering can be avoided in this case. And after this certain depositions, certain length of depositions, whole thing is again similar to MCBD technique. It is heated so that it can collapse to a solid rod preforms. Right. So that is the plasma activated chemical vapor deposition techniques, right? So in all these cases, preform is made, but I'll just show you how preform. Okay, let us see how preform. Before that, let us see how preform is used to draw the fiber. In this case, you see this is a preform. There is a preform. You see this is the preform that just I've discussed. It can be made through inside deposition process or can be outside deposition process. This preform is then heated through this furnace. This furnace is there, right? And you see whenever and it is pulled, I just mentioned when the glass is heated and it is pulled, then it will be a fiber can be made. Fiber is made, right, by pulling. So you see it will be a fiber, right? And actually, and there will be no cooling arrangement here because it is at very high temperature, say 1500 centigrade, and it is air, simple air. It will be solidified, right? And it is collected in this drum. So and the speed it is rotated. Drum is rotated, right? So depend upon this speed of the drums, you see the fiber diameter will vary, right? This take-up drum is there. This drum is rotated, and speed of the drums that will decide the diameter of the fiber. Now, how suppose you need certain diameter of the fiber, how can you measure? How can you select the diameter of the fibers? So immediately after the fiber is made, it is sensed through these sensors. Right, diameter sensor is there. I'll just show you in the left hand side. So need how the diameter is measured. So immediately diameter is measured, and that is used at the feedback systems. After measurement, and a signal is generated immediately after this diameter measurement. A signal is generated to adjust the speed of the drums, right? The speed adjustment is required to get the diameter equal to the desired diameters, right? Diameter obtained should be equal to the desired diameters, right? So there is a feedback system is here. So that will adjust, signal is generated, just immediately after the diameter measurement, a signal is generated, and that signal is used to adjust the speed of the drums to get desired diameters. Measured diameter should be equal to the desired diameter, right? So that is the from fiber drawing machines. Of course, here after this coating station, after this plastic coating station is here. Plastic coating station is here. Measure value equal to that even plastic coating is provided. Otherwise, it will not be on the flexible fibers. So coating is provided here. Fiber can be rolled, right? If it is made of glass, then it can break. And how diameter is measured, you see it here. The scanning element is here. This is a scanning element, right? Scanning element. A fiber is placed across this is laser source, laser beams, right? And this is rotating. This is not rotating. This is just scanning the diameters. So whenever there is no fiber, a signal is generated. But whenever fiber is placed, then at the edge, you'll get two pulses. One pulse just when you touch the fiber, one is another is when you just another. Refractivity variation will be there, so you'll get the two pulses at the detector. So by measuring the difference between this time difference between these two pulses, you can measure the diameter of the fiber. This is a laser scanning method. The different methods are there to measure the diameter of the fiber. But because diameter is of the micron, so ordinary screw gauge method, those things cannot be used. So that is the fiber diameter. Just 1 minute, I'm just taking one more method. This is a direct melting technique. In this case, you see there is no need of preforms. DD method, double crucible method is here. Here you see two crucibles are there. One crucible, inner crucible that contains the molten glass for core, and another crucible is here that is used for cladding. Right. In fact, initially these rods, they are the core feed rods and cladding feed rods. These rods are made from powder, a mixture of powders. Right. These rods are used as the feedstock materials, and high temperature furnace is here. Is at the you see it is placed. The crucibles, double crucibles, they are placed in the high temperature furnace, right? And so that it melts. These are melts. These are molten glass for the core. These are molten glass for the claddings. Now, and there is an orifice at the end. So whenever you see it here, there is nozzles. When the fiber is coming out through these nozzles, it will be a fiber, right? And very good GI fiber also can be made with this technique, because you see whenever the core glass comes in contact with the cladding glass, both are in the molten state, so that can be diffusion process, right? So because of these things, you see the refractivities can vary, right? In this case, the GI fibers can be meant. GI fibers, core should be of a particular varying refractivity should be there. So refractivities can be varied because you see the core glass, when it comes core material comes in contact with the cladding glass, that can be a diffusion process, right? So because of these things, refractivities will vary, and so you can have very good GI fibers. Of course, here the problem is these contaminations. Condensation process is here, so that is the drawback of these methods. I mean, lossy fiber can be. Fiber will not be of low loss, right? So these are the techniques used for these different techniques for fiber fabrications. Anyway, I'm stopping this one. So already time is over. If you have any questions, one or two questions, you can ask anybody.
Sir, this is also from that Ogata book, sir. Black cover.
Books you can have it. Black cover. All
Yes.
the figures you can have. Little bit different, but I mean just simplified diagram I have shown it, so that you can easily draw it. So that's what I have shown it. Everything's you can have it. Everything's.
Sir, one more question, sir. Like in this, we have to focus more on theoretical aspect or are there any numerical aspects, sir?
Theoretical aspect or numerical aspect means, I mean, here I have not discussed any theory here, only description. Here I have discussed only descriptive. What are
Yes,
the
sir.
different techniques? Theory,
Yes.
I'll discuss it next times. Theory.
Yes, sir. Yes.
Right. This is only description. So the different techniques I mentioned, materials, how the materials are used to fabricate the fibers. Right. Next time
Yes.
I'll just show you the next time onwards, I'll show you the ray optics method and mode optics method to design the fiber to define to find the fiber parameters, numerical aperture, V number, how we are saying how can I design a single mode fibers. Right. Those are actually based on theory. So that I'll discuss it next. What are the conditions or mode propagations? Those things are based on theory. That I'll show you next times.
Yes, sir.
This is so far I have discussed description. Okay.
Yes, sir.
Okay now. Any other questions?
No, sir.
Okay then. This much today. Next time we'll see it.